Okay, so the last example we're going to do is testing a parameter using binomial distribution. You're like, no, we never had to use it. Now we're going to use binomial. Yes, because it's really important because as you move on into your major and you do research methods and more research just on your own, especially those of you who plan to get a doctorate or a master's, you're going to do all of this on your own. So you have to know these like techniques. It doesn't happen often, but it will happen. So it's good that we just go over it a little bit. So let's go ahead and do that. So my little warning says, given a sample size n and the probability for success p, when this product is less than 10, we can calculate the p-value using the binomial probability. So the nice thing about binomial probability is that we're still able to complete the hypothesis test. This is really important because with a mean, and if we're given a sample size with a mean, when we're testing about a mean, that the sample size is smaller than 30 and we're not given raw data, so we can't even test it with box plots, there's nothing, we have to throw our hands up and start over and grab better samples. But with proportions, we have a solution. No matter if that product is greater than or equal to 10 or is less than 10, we have a way of going and completing our hypothesis test, which is really valuable and less time consuming. Okay, so in this example, it says 10.5% of all live births in the US were to mothers under the age of 20. A sociologist claims that births to mothers under 20 years of age is decreasing. Okay, the sociologist conducts a simple random sample of 34 births and finds 3 of them were to mothers under the age of 20. Test the sociologist's claim at the 0.01 significance level. So notice that they didn't give us any information. So we're gonna about the population. So we have to go ahead and do some preliminary. So let's go ahead and do that. So the preliminary for proportions says that the sample size n equal to 34 because that's the sample we took, and that so n is 34, and the population proportion of mothers under the 20 years of age is 10.5%, so 0.105. So the first preliminary is if the sample size is no more than 5% of all U.S. Mothers under the age of 20. Yeah, because there's a lot more than 34 people having kids under the age 20, right? So definitely that is met. So we can assume that samples are independent. The next piece we said is that product, right? NP times 1 minus P should be less than or equal to 10. So let's go ahead and test that. Let's do 34 times 0.105 times 1 minus 0.105. So I'm just going to go to my calculator and put 34 times 0.105 and then times 1 minus 0.105. So that is 3.19515. 3.19515. So let me scroll down a little bit more so we can see it here. That is definitely less than 10. Yikes. That just means we can't assume that the distribution is normal from the population and that we just go ahead and defer to a binomial probability. So essentially finding the p-value will just be like the binomial distribution in our calculator, not the t-test or one prop z-test. Okay, that's it. And then we can go on to the test. So this just allows us with proportions, just tells us which test are we going to use, binomial probability or the one prop z-test. And if it's less than 10, we use the binomial probability. Okay, so let's go ahead and continue with the hypothesis test. So the first step always, H sub 0, right? Set up your hypothesis. And we're doing a proportion, right? So don't lose sight of that. So P. The population proportion was 10.5%. So status quo would be 10.5%. But the researcher says that he or she believes that the number of mothers under 20 years of age is decreasing. So what does that mean? Decreasing would be a larger proportion or smaller proportion, right? Smaller, and then mark the claim. So what type of test is this? So going on to step 2, we can see that it's pointed to the left, so it'll be a left tail test, right? Where the alpha given is going to be 1%, 0.01. So if it's a left tail test, let's go ahead and mark that. Right, and that's where alpha is 0.01. And then because we're dealing with a proportion, this would be some negative z-score, whatever. We don't really, we're not using the z-score, so that's okay. We just need to know that tail is alpha. And then here is that population parameter of 10.5%. Okay, so step 4 would be the p-value. So let's go ahead and find that. And let's write a note. So because NP times 1 minus P was less than 10, we are using the binomial distribution. Right, and you should remember it as binom CDF in the calculator, right? NPX. Okay, so let's figure that out. What are we looking for? So we're looking for the probability that the value or proportion of mothers is decreasing, and that would be less than or equal to how many births. So let's go ahead and let's note some stuff on the margin. Let me go ahead and choose a different color, green. So we know that we took a sample of 34 births, and the researcher found that 3 of those births had mothers that were under the age of 20 years. So if we want to find the probability that, test the claim that this is decreasing, this rate, this means we're looking for the probability that a randomly selected individual sample would have less than or equal to 3 births in which mothers were 20 years or younger. If it was increasing, we would say, okay, we're looking for a randomly selected individuals where it was greater than having 3 births, right, of the sample. So we're going to use this 3 as the barrier, because either in that randomly selected sample, either 3 of them are going to have all 3 will have mothers 20 years or younger. 2 of them will and 1 won't. 1 will and 2 will have mothers older than 20. So we're going to do a binom CDF to add up all those probabilities. This is nice because remember, binom CDF includes the endpoint. So we could go ahead and go directly to setting it up. So we have binom CDF of NPX. So our N is 34, that's our sample size. It's 0.105, right? That's our proportion population, and then 3. So let's go ahead and put it in the calculator. The binomial distribution is in the distribution second vars, and remember it was B. And so we had 34 births, and the probability that those births had mothers younger than 20 is 10.5%. And we found 34 mothers had mothers, three of those births had mothers that were 20 years or younger. Okay. And so we get 0.51, well, around 4 decimals, so 0.5149. So this probability is the actual p-value. There you go. So if we want to compare now this p-value, so let me go ahead and do it now. So p-value is equal to 0.51 and the alpha was 0.01. So if we compare, is the p-value going to be larger or less than alpha? Definitely larger. So here, if we go back to our picture, this p-value is more than 50%. So it's going to be like right here. That's the p-value. So the likeliness I grab another sample and that sample will have something different or that probability will be less than alpha is highly unlikely, and therefore we're going to keep status quo. And so therefore when the p-value is larger than the alpha, we'll go ahead and not reject the null. Okay, so if you do not reject the null, that means you keep the null. And what does that mean to the alternative? Okay, well, I cross out the alternative. That was the claim. So if we keep status quo, do we have enough evidence to support the researchers' claim that that proportion has decreased? No. So we would say something like, in step 5, there is not enough evidence to support the researchers' claim that the proportion has decreased 10.5%.